In this video, we will be looking at how to describe the position and orientation of objects in a robotics system. This would include parts, tools, and even manipulators. These spatial descriptions would later allow us to calculate linear and rotational velocities, forces, and torques for the robot links. So the first step in finding the whereabouts of any robotic manipulator is to find its position in 3D space. Any position or a point is given with respect to a world or a universe coordinate system, and in this case it's denoted by the letter A. The position of any of these links for the robot shown here or the end effector is given using a position vector and is denoted by PA. There can be multiple position vectors or even other coordinate systems such as the one shown here defined for this joint. Let's call it B. Now all these coordinate systems and position vectors would eventually link back to the world or the universe coordinate system. Due to this, the notation PA is used, where A shows the reference coordinate system and P shows that it is a position vector. If Cartesian coordinates are used, the position of a point in space can be given through its x, y, and z components. Along with the position, the orientation of the manipulator must also be described. This shows how it is angled or oriented in space. Here, a coordinate frame B has been assigned to this end effector. It shows how the x, y, and z axis are set for this particular part of the robot. Using this, the orientation of B can be expressed relative to any previous coordinate frame, in this case A. Numerically, the orientation is expressed using a 3x3 rotation matrix, which comprises of a stack of the unit vectors in the x, y, and z directions going from B to A. The notation RAB shows the orientation of B relative to A. This notation is very important and would be used extensively throughout this topic. By combining the orientation matrix and position vector, we can now fully describe the whereabouts of any robotic manipulator. This is known as a frame. Note that the frame is just another coordinate system where the position of its origin, in this case B origin, and its orientation are known with respect to a previous coordinate system, in this case A. Take a look at this diagram. You have three frames. You have frame A, B, and C. This is quite similar to a simple robot with one joint and a tool. The base of the robot would correspond to frame A, which would also be the world coordinates. The joint would be frame B, and the tool would be frame C. Through this, you can see that we know frame B relative to A, and we know frame C relative to B, but we do not know frame C relative to frame A. This, however, can be calculated using a transformation matrix, which I will go through in the next few slides. So now that we know how frames operate, we can map vectors from one frame to another. And when doing this, there are three main cases. The frames can be translated, they can be rotated, or a combination of both. In this case, we're looking at only a translation. A point is defined in frame P and it has position vector PB. frame B has the same orientation as A. It has only been translated by some amount, and this is shown by the position vector PB origin with respect to A. So practically what you can get from this position vector is the amount the origin of B has been translated with respect to A. If we wanted to express this point in terms of frame A instead of B, we can simply find our PA, and this would be done by taking the sum between the two vectors. So we have our P B origin to A, we have our PB, and the resultant between these two vectors would be RPA. So what you have to understand from this is that the point in B has not changed, only its description has changed. We are now describing it relative to a different frame. The second type of mapping are rotated frames. Here, frame B has been rotated with respect to frame A. The orientation of B is now different to that of A, yet there is no translation as the origin of B has not changed. A point in frame B can be represented in frame A using the 3x3 rotation matrices as discussed previously. This would sum down to these three matrices depending on how frame B was rotated in the X, Y, or Z directions for an angle of rotation theta. So the point in frame A, PA, would be the rotation matrix times the position vector PB. Note that this rotation matrix can be a combination of these three matrices in any order. So for example, RAB could be equal to a rotation in the X direction, followed by a rotation around the Y-axis, and then maybe another rotation around the X-axis. The minus signs used in these equations depend on the convention used. For my videos, I have taken a counterclockwise rotation as being positive. So up to this point, we have seen how frames can be translated and rotated separately. But in a typical robotic system, you're going to have multiple translations and rotations about all three axes, and this would allow us to properly orient and move a tool to its desired location. An example of that is shown here. So if you look at frame B, you can see that it has been rotated and translated by some amount with respect to frame A. Now for ease of use and by convention, we can represent both the rotation and translation in a single 4x4 transformation matrix. So the transformation matrix would comprise of the 3x3 rotation matrix, the position vector for the translation of the origin of B, and the fourth row would just have 3 zeros and a 1 to complete the matrix. Now we have the same scenario. We have a point represented in frame B, and we would like to express it in terms of frame A. To do this, you can simply multiply the transformation matrix with the position vector in frame B. A simple trick that I use to easily remember this is that the frame given here should match the frame here. And if that is the case, the frame here would be the frame that the answer is given in. And if you look at it, it kind of makes sense, because this transformation matrix shows the transformation of B relative to A. And so it makes sense that we should multiply it with the position vector in frame B, and we would get the position vector in terms of frame A. Alright guys, so that's all for this video. If you guys liked it, please click the like button below. If you have any clarifications or questions on position vectors, orientation, or transformation matrices, please leave a comment and I will do my best to get back to you. I hope this video helped, and if you haven't done so already, Please subscribe.